Well, hello. Welcome to Ron Academy. Today we are going to start on the fundamental principle in thermodynamics called property relationships. There will be a variety of ways that we look at the property relationships, but perhaps the most extensive will be in the steam tables. Now, the steam tables are a generic term for tables in the back of our book where we can find properties of steam, also known as water, but also properties of various refrigerants, ammonia, propane, air. So we're using the steam tables, but steam tables is beyond steam. So you definitely want your book. If you do not have your book, you're going to want to go and get it. I'll try and remind students before watching this video to get a thermodynamics book. I am using Moran and Shapiro's 6th edition, Fundamentals of Engineering Thermodynamics, and I would recommend that you do the same. So I'm going to start by talking a little bit about the tables. This is page 815. Now page 815 describes all of the tables. It's the index for the tables, A1, A2, A3, A4, all the way down to A27. As I mentioned, we'll see water here, water, water, water. Also see refrigerant 22, refrigerant 134A, ammonia, propane, air, and some other gases. First thing to note, other than page 815, is that the book comes in the tables come in two forms. SI units, and that index is on page 815, and these are tables A1, A2, A3. And then, a few pages later, we have the table in English units. So we have the index to tables in English units, and this is page, just take my word for it, 863. Page 863. Now these tables are identical tables, except they're in English units, and we see A1E instead of A1, A2E, A3E. So if you're in English units, you use the E tables. If you're in SI units, you use the regular tables, the non-E tables. All right, I'm going to set the book aside and talk about how we use the steam tables to find different properties. I'm going to draw a diagram that we've seen before, temperature entropy diagram. Everybody might remember what this thing is called. What is it? The vapor dome. Now, I'm going to draw a line of constant pressure. So everywhere on this dashed line that I'm drawing, the pressure is the same. And I'm going to define this pressure as 14.7 psia. So I'm in English units. Again, there are 5 different phases. Everything to the left is a subcooled liquid. Finding the properties of subcooled liquids will be its own video. Right on the vapor line, we call that a saturated liquid. On the vapor line, a saturated vapor. Everywhere in between is a wet vapor. And everywhere to the right is a superheated vapor. So I'm going to ask you to turn to table A2E, and I will do the same. So this is table A2E. The important things to note are the name of the table, its properties of saturated vapor. So that means it's going to work for us everywhere from from here to there. We have saturated vapor from saturated water from liquid through the wet vapor all the way to the saturated vapor. So that's the first thing. We're looking at the name. The second thing is look at all the different properties that we can find here. Specific volume, internal energy, enthalpy, and entropy. So we've got 4 different kinds of properties. The third thing to look at is these 2 columns right here, temperature and pressure. Now temperature and pressure are special. They go together. For every pressure, there is exactly 1 temperature where water boils, and that is, and everybody knows it, 212 Fahrenheit. So I look at the next page, page 866, and I see when the temperature is 212, that the pressure is 14.7. So now I can find things across this list. So for the saturated liquid, we use a subscript of F. So you will, if let's stick with enthalpy, it's all about the H. So if we find H sub F, and we can do that right here, H sub F, right above that it says saturated liquid. For 212 and 14.7, H sub F is 180.2. And notice that the units are up there as well, BTUs per pound. BTUs per pound. We also can find saturated vapor. Now notice that they use the subscript G for saturated vapor. So Hg is 1150.5 BTUs per pound mass. Now let's think about what that means. It means that the amount of enthalpy that a pound of water has as a liquid, amount of energy that it has, is 180 BTUs. If I want to bring it all the way through the vapor dome and convert it completely from a liquid to a vapor, I would have to add whatever the difference is between 1150.5 and 180.2 BTUs for each pound, and that would bring it out here to that point. In fact, it turns out that that amount of energy is a name we've heard before. It's the latent heat of vaporization. It's how much energy does it take to go from a liquid at saturation to a vapor. It's so common that they even put it in the table. It's the middle column for enthalpy, and they signify it HFG, and all it is the difference between those two. They've just used a spreadsheet to do that subtraction for us. HFG 970.3 BTUs per pound mass. I'll check on my time and see if we should move to a new video or not. I think we'll take this one step further. So the question that I would have if I were a student is, okay, we can find the enthalpy here, and we can find the enthalpy there. This is HF, this is HG. We can find out how much energy it takes to go from here to there. But what if I wanted to find the enthalpy somewhere in between? What if I wanted to find the enthalpy right there? Well, we call that quality. So let's say that I'm 25% of the way from saturated liquid to saturated vapor. The quality then would be 25%. If I were 75% of the way, my steam would be 75% quality. And we talked about this in a previous video. Well, how can I find the enthalpy for a wet vapor? Well, basically all I have to do is start at ground zero and come up to saturated liquid. We call that HF. Plus, now I need to take 25% of the difference between these 2 points. So plus the quality, in my case 25%, times the enthalpy difference. So if I wanted to find the enthalpy here, I would say 180.2 plus 25% of 970.3. And I could do this for anywhere in that wet vapor region. All I would have to replace is a different quality. So, as a review, in this video, we've identified the different kinds of tables, metric and English. We've started using the saturation water table, table A2E, and we found enthalpy. We could do specific volume or entropy or internal energy as well. It's all the same. For a saturated liquid, a saturated vapor, or anywhere in between. One more thing before we stop, and that is to bring up what is table A3E. It turns out that table A2E and table A3 are identical tables. The only thing that changes is whether temperature is in the first column and pressure in the second. We call that the temperature table. Or if pressure is in the first column and temperature in the second. I'm going to move my paper out of the way. I'm going to take a look at what table A2E is called. It's called Properties of a Saturated Water, the Temperature Table. And notice in the first column we've got temperature. And it's got nice markings. We go 35, 40, 45, 50, 50, and then we go by 2s to 60 to 70 to 80 to 90. Then we start going by 10s again at 100. Nice even temperatures. Now we flip to table A3E. Same information, except it's the pressure table. Pressure is first. And it's got nice increments, 0.2, and then 1, and then we switch to 5, and then we switch to 10. We zero right in here at this special one, 14.7. They've even brought it to a few more decimals. And we get the boiling point of water to 11.99 or 212. And if we look over here, 970 again is the HFG, 180 is the HF, 1150 is the HG, same table. These are the saturation tables. They're good for anywhere on the vapor dome or inside. That's good enough for now.